Can you see my screen?
Yes, sir.
Okay, let's do semiconductors then. Okay, I don't know how many of you have joined. Okay, and you guys are not responding right in the group properly. So yeah, let's start with online only. No, offline, let's see later when the things are okay. It's very cold also these days, no? Okay, see. So let's start with this. Okay, all the needed things I'll do, okay, from semiconductors. This is mainly conceptual. This chapter is very conceptual, okay, and then you don't have derivation here, okay. We don't have no derivation, okay, no derivation. So it's a very easy chapter to score marks, okay. So you can score marks from this chapter. Okay, we will discuss all the board questions, okay, one by one. I'll tell you what are the important ones, what are not so important, and everything, okay. So let's start, okay. See. In atoms, okay, in atoms, I don't know whether you have attended or not. In atoms chapter, okay, do you remember we have done hydrogen atom, and we have learned something there very important, okay. Do you remember, guys, that in hydrogen atom, right, how many atoms, how many protons we have in the nucleus in hydrogen? We have one proton, okay, and we have the orbit, right? Here we call it n equals to 1. We also have another name for it. We call it what state, guys? We call it
ground state.
Ground state, yes, okay. And we have electrons present in the ground state. The first state, right, available for the electrons, we call it ground state, and the electron is present there in normally in any hydrogen atom, okay. If you remember, is this the only level present, or there are more levels also for the electron that can be occupied?
There are more levels.
There are more levels, no? If you remember, we started with n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, and so on. No, we have many levels, okay. If the electron is present in the ground state, we have to show one dot here like that, no, showing that one electron is present here. If I tell you that the electron is here, what does it mean, guys? The electron is in the ground state or first excited state?
First
excited state, okay. Can you tell me just roughly what is the energy of the first level? Anybody who remembers energy of the first level in a hydrogen atom? You know this one, minus 13.6 electron volts. I don't know if you have forgotten, okay. Then E2, anybody remembers the value of E2? Minus 3.4 electron volts, no? So what basically I'm trying to tell you is this, okay, that the electrons, right, whenever they are present in an atom, no, they will have some energy levels. They will be present either here, they will be present either here or here or here. The electrons can be present in any of these levels. In the ground state, obviously electrons will be present here, okay. Now why am I talking about this, okay? Try to understand. See, I'm going to draw one metal now, okay. Check. Don't forget our topic is semiconductors, and semiconductors are those substances which are exactly between, okay, which have properties exactly between what and what? Conductors and insulators, okay. Semiconductors, they are not fully insulators, they are not fully what? Conductors, but they have properties in between what and what? They have properties in between conductors and insulators. You can give me examples. Let's start with examples, guys. Conductors, give me examples.
Copper wire.
Copper, okay. Then
silver
aluminium,
wire.
silver, Ag, yes, okay. Silver, aluminium also I've written. Sodium, Na, okay. Insulators, can you give me some examples of insulators?
Plastic.
Wood, okay. Wood, we have wood. Plastic, okay, agreed. Plastic. Best insulator, you're not telling me till now. Who's the best insulator? Current cannot pass at all, huh?
Rubber,
but it's not the best. Best insulator, who knows about best insulator? Yes, air. It's an insulator or conductor? Insulator. If air was conducting right now also, you'll be getting shock, no? While sitting in your room, somebody switches on the light, you will get shock, okay. But don't worry, air does not conduct, so it's an insulator, okay. What is the property of all of them, do you know? And what is the property of all of them? They have something and they don't have something. Who can tell me? Conductors, they have what?
Free electrons.
Very good.
Ions.
They have free electrons.
electrons.
Free electrons. They have free electrons, and these insulators, they do
Don't
not have free electrons. Okay. What about semiconductors then? What do you think? They have free electrons or they don't have free electrons? What do you think? Semiconductors. Example, anybody knows the example? By now you have studied, no, in your school maybe? Example of semiconductors is what?
Germanium and silicon.
and silicon. Yes, germanium and silicon. Both of them, they have something common. Can you tell me what is that? They are both present in which group?
Group 14.
Group 14. Okay, group 14 or group 4, no, we call them, right? Okay, you know why? Because the valency of germanium and silicon both have how much valency? Valency of 4. Okay, both of them, they have valency of 4, and they do not have free electrons. Okay, but sometimes, okay, not sometimes, there are situations where they will also have what? Free electrons, and there are times that they don't have what? They don't have free electrons. Sometimes they have free electrons, sometimes they don't have free electrons. So sometimes what happens? They behave like what? Insulator, and sometimes they behave like what, guys? Conductors. Okay, so they are called semiconductors, no? Like not very good conductors also, but somehow or somewhat they manage to conduct also. Okay, we'll be talking about them. Okay, germanium and silicon. So now look at the picture. Okay, I'm going to show you a picture which is called energy band diagram. Okay, look at this. I'm writing something called energy band diagram. This is important because it's the beginning of your chapter. Okay, I do not know your teacher has done or not, but we should do it. Okay, see, I'm going to start with, let's say, aluminum. Okay, check. Okay, this is applicable to all the metals. First I'll talk about metals like your aluminum, then I'll go to, okay, I can easily go to your insulators, and then I'll come back to your semiconductors. Okay, so this is an atom of aluminum. Okay, check. If you have doubts, you can ask me. So in the nucleus of aluminum, okay, what is the atomic number, guys? 13, no? So that means it has how many protons? It has 13 protons and it has 13 electrons. Right now I'm not even talking about neutrons, not needed. Okay, so in the nucleus of aluminum atom, how many protons will be there? 13 protons. I think you're clear with this one, right?
Yes, sir.
Okay, now look at this. Okay, I'm going to draw one level here. See, not level, but let's say an orbit. What is this orbit called? I think you know already by the name, by now. What is this orbit called, guys? This is n equals to how much?
1.
1. How many electrons can sit here?
2.
2 electrons. Very good. Okay, and you know what is this? This is called 1s, right? Okay, what is the second orbit? Second orbit has how many orbitals, guys? Who can tell me? Second orbit has 2 orbitals. Very good. Who are the 2 orbitals?
S and P.
S and P. Yes,
S and P.
2s and
2p.
2p. Okay, in your s orbital how many electrons can be added? 2, right? But p orbital how many electrons can be added?
6.
6. So total how many electrons can be added in the second orbit? 18 or 8? 8 electrons. Okay, look at this. Yeah, look at this. I'm drawing the second orbit now. Okay, this is n equals to 2. Okay, so how many electrons should I draw, guys? 1, 2, 3, 4, 5, 6, 7 and 8. So total how many we have already written? Let me write the configuration also. 2, 8, 3. You have seen this. Okay, we call it electronic configuration. This is how electrons are arranged. First orbit, second orbit and third orbit. The third orbit, do you agree that it is the outermost orbit or not? For aluminum, the third
Yes,
orbit is called the outermost orbit. We have another name, right? We call it what, right? What, guys? We call
Valence.
it valence or valency or valence shell?
Valence
shell. Okay, now tell me how many electrons are there in this valence shell? 2 already written, 8 already written. Now how many? 3. Okay, so I'm going to draw 3 electrons. Look at this. This is the first electron, second electron and the third electron. So there are how many valence electrons? Valence shell has 3 valence electrons. Are you clear with this, all of you?
Yes,
outermost electrons. Yes. Okay, this is very easy, right? So now you are thinking, what am I trying to do, right? Okay, let me tell you what am I trying to do here. See, you will also agree with me, right? This outermost electrons in a metal, they are also called what electrons? Free electrons. They are the ones which are free electrons. Okay, these inner ones are not free. These are the outer ones which are free. They can go from one atom to any other atom. Okay, that's why we call them free electron. Okay, now if I take a solid of aluminum, check what will happen. Okay, if I take a solid of aluminum, this will happen. Okay, I will have one aluminum atom. Will I have another one also? Yes. I'll have another one nearby. Okay, will I have another one? Yes, I'll have another one nearby. Because in a solid we'll get only one or many atoms. We'll get many atoms, no? So like this, see, this is a picture of any aluminum solid. Okay, so that's what I'm trying to show you here. See, we have many aluminum atoms, all are almost identical. Okay, now check. So I'm taking a solid right now. Let's be clear. Okay, let's talk about this solid, whole aluminum solid I'm taking, and now I'm going to arrange, okay, all the electrons in their respective energy values. Okay, so look at this. This is the bottommost energy, or let's say ground state. Let's call it E1. Okay, now think and tell me. Okay, looking at this atom here, which electrons here, okay, has the lowest energy, guys? The electron in the first orbit, second shell, or the third shell?
Third shell.
Third shell? No. These are outermost electrons. They are the most energetic. Which electrons are very stable here, guys? Which one? Electrons present in the outermost or the innermost? Stable electrons. Innermost. So this electron, look at this. This electron here, right? Okay, they are the ones. They are the two of them, right? This one, and this one. They are present in the innermost orbit, and they are the most stable electrons. Okay, so look at this. Do you agree they will have energy or the lowest energy? Lowest energy. So that's why look at this. I'm coming back here, and I'm talking about the E1, which represents lowest energy. And I'm going to put here how many lines, how many dots? You know, 2 dots. Why am I putting 2 dots, guys? Because
there are two
electrons which have this energy, right? Okay, then I have another level here. Okay, I have another level here, which is called what, guys? We call it what now? E1 or E2? E2. Okay, then I have another one. I will call it what, guys? E3. This represents level of energy, right, for all the electrons or valence electrons. This represents energy level, no? I'm repeating again, huh? This represents what? Energy level for whom? For outermost electrons. These are the ones for those 8 electrons. How many dots should I draw? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Can you understand what I'm trying to do here, guys? I'm just arranging. See, these 8 electrons, they have energy. Yes, they have energy. Do they have same energy as this innermost, or they have more than them?
More than.
So they have an energy called E2, which is greater than what? E1. Yes, and that's why I'm drawing them here. I think you understand this right now. Yes or no? Okay. Yes. Okay. Then look at the third level. Okay, the third level, how many electrons they have this energy, guys? What do you think? In the third level, how many electrons? 1, 2, and 3. Okay, these 3 electrons should be somewhere here. 1, 2, and 3. Are you clear with this till now?
Yes, sir.
Okay.
Yes, sir.
Okay. So I suppose this till now it is clear. Okay, so I've just arranged them, right? Only for one atom I did it. Okay, now I'll do for the next atom. Look at this. Now when I take the second atom, this is the second atom in this entire solid. Okay, second atom in the entire solid. Do you agree that this is also aluminum atom or not? Yes, this is also aluminum atom. You'll also agree with me that in the first shell we have how many electrons? 2 electrons. These 2 electrons also will have energy, right? Where do you think these 2 electrons will have energy, guys? E1 or E2?
E1.
E1. Somewhere here. See, again I've drawn it. Okay, let me remind you, I have drawn it here, okay, for the second atom. Okay, and it is not compulsory to have exactly same amount of energy as these 2. They may have little bit slightly different amount of energy. That is okay, possible, but more or less it will be nearby this first energy level. Okay, even for these 8 electrons, look at this. 1, 2, 3, 4, 5, 6, 7, and 8. These electrons are in the second orbit of your second atom, second orbit. So these electrons I should arrange here, right? Somewhere here. 1, 2, 3, 4, 5, 6, 7, 8. I think you can understand, right? You can see, right? I'm making the dots, right? So they will belong somewhere here. Okay, and again this 3 electrons, 1, 2 and 3, the outermost electrons in the second atom of aluminum again will be somewhere here. See, 1, 2 and 3. Can you understand? So what have I done, guys? Am I drawing energy levels for only one atom, or for I'm drawing for right now I've drawn for two atoms?
For 2 atoms.
For 2 atoms I have drawn. Like this, what will I have to do? Tell me. Will I draw it for only one of them, 2 of them, or all of them?
N times.
N times. Yes. We are going to do it. Okay. Automatically you will see. Okay. See. Just now I told you, no, that this is third level. I'm just drawing some lines here. Okay. I'll tell you why am I doing that. In the third level, I'm just drawing some lines. I'll tell you the reason. Okay. Check. Let's look at the third atom. Okay, forget about these inner electrons. I'm not worried about them. They will be somewhere here and they will be somewhere here. Okay, our main intention is this valence electrons, because they are the one which will give us electricity, the valence electrons. Now let me tell you. See, this is the outermost electron, outermost electron, outermost electron. In the third atom, it will have energy level very close to these electrons which I've already drawn. Can you understand? I did not say equal. Did I say equal or almost same energy, guys? Can you answer what I'm doing? Guys, did you answer what I'm doing?
Sir, can you please repeat?
I'll repeat. Okay, this is an, what is this, guys? It's an electron where? In the outermost shell or not? In the outermost shell. Do you agree it must have energy equal to E3 or not?
Yes, sir.
Yes.
But in a solid, it is found that the electrons cannot have what? Identical set of energy. You have heard about this also. Have you heard about this principle in chemistry? No two electrons can have same set of all the quantum numbers equal. Have you heard about this rule?
Yes, sir.
Even if they do, they must have opposite spin. Have you heard about this one?
Oh, yes, sir.
No. Okay. You know what this opposite spin does? One spins clockwise, one spins anti-clockwise, and still, you know what? Some of them will obviously have what? Little bit of different energy than the other 3. Okay, so what I'm trying to tell you is this. See, this is the third outermost electron, this is the outermost electron in the second atom, these are the outermost electron in the third atom, these are the outermost electron in the fourth atom, outermost electron in the fifth atom. My point is this: do you agree that all of them will have same energy or almost same energy?
Almost same energy.
Almost same energy. That's why. Do you get a particular line, or you get here many lines or many levels?
Many levels.
Many levels. Very good. Okay, that is what I'm trying to tell you. Okay, so now, but at least you can understand who belongs here. All the electrons are only the valence electrons.
Valence
Valence
electrons.
electrons. Now listen. I'm going to define to you something. Okay, look at this. Do you agree that I can group all of them together, right? I can make a group out of all of them, right? Yes or no? This
Yes,
group.
sir.
Okay, look at this. Okay, this group of what? This is a group of electrons. Actually, not group of electrons. These are group of electrons or group of energy levels.
Group of energy levels.
Energy levels.
Group of energy levels. This is a group of energy levels for all the electrons or only for valence electrons?
Valence electrons.
Valence electrons. Okay, valence electrons. And this group is called valence band. Are you clear what is called valence band?
Oh, yes, sir.
Okay, so tell me what
Yes.
is a valence band, guys? Tell me what is a valence band?
It is a
Group of energy
levels.
Good, very good. It's a group of energy
Energy
levels. Okay, and energy levels for all the electrons or only the valence electrons?
Valence
Only valence
electrons.
Only the valence electrons. Are you clear, all of you? Sure.
Yes, sir.
Okay. Is it clear for all of you? Just check, all of you guys. Respond. Otherwise, it will be boring. You know, online classes are boring only. Okay. Now check. Okay. Now check. Very, very important. Above this valence band also, okay, there are levels. I'm repeating again. Above this valence band also, what are there, guys? Energy levels. Okay. Group of energy levels. Let me say like that. There above this valence band also there are energy levels greater than valence band energy levels. Okay. And this energy level or this group of energy level, we have a name for it. Okay. We call it conduction band. What do you call it? Conduction
Band.
Can you understand what is conduction band? What is conduction band also? It is also what? Energy level or group of energy levels?
Group of energy
Group of
levels.
energy levels, okay. And who will stay in this conduction band? Tell me, who can tell me?
Electrons which are being excited.
Not necessary right now, but you are almost right. Who will stay in this conduction band? Those electrons, I'm repeating again, those electrons which can what? Conduct
Electricity.
conduct which electricity, okay. So those electrons which can conduct what? Those electrons which can conduct electricity, their energy levels will be in a band. We call it what band, guys? Conduction band. Are you clear with this?
Yes, sir.
Yes, sir.
All of you clear? Sure, clear.
Yes, sir.
Okay, now let me come back to the main point. Okay, I'm talking about metals, metals. I'm going to go to insulators also. I'm going to talk about metals right now. Look at metals. Metals are so nice. Why? I'll tell you. Look at this. This is a conduction band. The conduction band and the valence band, they overlap. Look at this. Conduction band. Let me write it down. Okay. Conduction band. And which band, guys? I told you. Valence band. What do they do? They are separated or they overlap?
Overlap.
Overlap. And you know what does it mean? I'll tell you. Overlapping here means that those electrons which are in which band, guys? In the valence band, in a metal, they are also responsible for what? They are also responsible for
Conduction.
conduction of current. Therefore, they are also present in which band? So those those electrons which are present in valence band of a metal, they are automatically also present in which band, guys? Conduction band, and they can conduct electricity. I'm talking about them only. Look at this. Yeah, this electron, this electron, this electron. Tell me, where are they present? Are they present in valence band? Your answer is yes, they are present in valence band. Do they conduct electricity? Yes, they conduct electricity. That means they are also present in which band? Conduction band. Okay, and this is the most important part. If somebody asks you, okay, this question, this is a valence band, VB in short we can call it. And what is this? This is conduction band. What you are going to do is you are going to show that the valence band and what, guys? The conduction band, they always overlap. That means electrons present in the valence band of any metal, they are automatically also present where?
Conduction
in the
band.
conduction band. Are you clear with the metals, guys? Is it okay or not?
Yes, sir.
Okay, now let's talk about insulators very quickly. Okay, see, for insulators this happens. See, this is a valence band of an insulator. Do we have electrons, guys? Yes or no? Tell me. In an insulator?
Yes, sir.
Yes. Obviously, outermost electrons we will get only, no? They may be free, they may not be what? They may be free, they may not be free. Okay, but we have a valence band and there are electrons in the outermost shell and they have energy levels, they have energies. Okay, but look at this now. What am I drawing now? Check. What is this band? This is conduction band. Okay, I'm talking about insulators right now. For insulators, let me tell you, okay, for insulators it is found that this conduction band is empty. First of all, what does it mean? Empty conduction band. Are there electrons or no electrons in this band?
No electrons.
No electrons. There are no electrons in this band. What is the meaning of no electrons present in this band? That means no electrons are present which can conduct current. Okay, and look at this. I'll show you one more thing. Check. What is this called? Will I call it conduction band or the bottom of the conduction band? Bottom of conduction band. Okay, what is this? Top of which band?
Valence band.
Valence
band. Okay, this, don't forget, as I go up, right, what increases? Do you agree that energy increases when I go up or not in this diagram, right? These are energy level diagrams, right? All these are energy values here. Okay, so my question is this. This is the bottom of the conduction band. This is the what? Top of the valence band. And this gap in energy between the bottom of the conduction band and top of the valence band, we call it energy gap. Can you understand what is called energy gap?
Yes, sir.
Yes, sir.
Okay, so what is energy gap? Tell me guys again.
It is the distance between the
Not
bottom
distance, not distance. Band gap. What is energy band gap?
The space between the
Not space,
bottom.
not space, not space. Is it the space or is it the energy gap? It looks like a
Energy.
space, right? But it is actually representing what?
Energy.
Energy gap between what and what?
Bottom of the conduction
Bottom
band.
of the conduction band and
Top
top of the
band.
valence band. This gap is known as energy gap. And let me tell you, in insulators, this energy gap, EG, is very, very large. Is very, very what? Large. Now you tell me, what is the meaning of very large gap?
It can't conduct electricity.
It can't conduct electricity is correct, but can anybody tell me in a different way, what is the meaning of very large gap? If I tell you this gap is very, very large.
It cannot overlap.
Electron to go to the
Electron
conduction
will
band.
not go
Electron cannot go from where to where?
from valence band to conduction band.
Okay, did you understand? All of you, did you understand what I'm saying?
So can you repeat?
I'll repeat again. See, if this energy gap was very little, I'll give you an example. Let's say only 0.1 electron volts. Okay, very little amount of energy gap. You think and tell me, huh? You know what does it mean? If the electrons, right? Don't forget, the electrons are present here in energy levels or not? Yes, they are present in energy levels. Can they go up? Can they go up? Yes,
Yes.
they will go up if they receive energy or not. How can they go up, guys? If they receive
Energy.
energy, electrons will go from where to where?
Valence band
band
to conduction
Conduction
band.
band. And what is the meaning of going from valence band to conduction band? Who can tell me? Going from valence band to conduction band means they will be stuck with the atom, or they'll become free.
They become free.
They become free. So electrons can jump from valence band to conduction band, and once they do that, they are going to become free. Okay, but the energy requirement is also there, right? If the energy gap is very little, this can happen every time and no problem at all. Okay, but just now I told you, right? In insulators, the energy gap is large or very, very large.
Very, very large.
So you tell me now, can the electrons easily go from valence band to conduction band, or very difficult to go?
Very difficult to.
Very difficult to go. Why? Because they need energy, or they need a lot of energy?
A lot of energy.
A lot of energy they need to go from which band to which band, guys?
Valence band to conduction
Yeah,
band.
this is a picture for whom? Tell me. Any conductor, or it is a picture of any insulator? Okay, now all of you think and tell me, huh? Do you understand, guys, what is the difference between a conductor and an insulator?
Yes, sir.
Okay,
Yes,
in an
sir.
insulator, tell me what happens. Or in a conductor and insulator, tell me in terms of band gap.
Energy gap are less in conductors.
Energy gap is less. Okay, will you agree that is there any energy gap or no energy gap?
No energy.
No energy.
No energy gap. Yes, easily the electrons which are here can easily go there. No, not a problem at all. But in an insulator, the energy gap between what and what? The conduction band and
Valence
band.
band.
This gap is very, very large. That's why shifting electrons from here to here is not possible. Okay, it's very, very difficult actually. Okay. Okay, I can give an example. When does this happen? Okay, in air also it can happen. See, electrons can go from where to where? I'm talking about air. Okay, air is an insulator. Electrons can really go, okay, from where to where?
Valence band to conduction band.
But you know when does it happen? I'll tell you. During lightning. You know lightning, no?
Yes, sir.
During lightning, what happens? Even the air conducts electricity, no?
Yes, sir.
Okay, that means the electrons are going from where to where?
Valence band to conduction.
And what do you think? What kind of potential difference is present with lightning? Very high potential difference. 10,000 volts. I don't know. Million volts maybe. Just imagine. Million volts of energy is required. Just imagine. Such a high energy is required to shift electrons from valence band to conduction band if it is an insulator. Okay. So obviously, right, we will prefer what? If you want to pass current, we will prefer conductors, because we don't have to apply such a high voltage. No, we can apply 1 volt, 2 volt, and electrons can start moving. Okay. Okay, that is a different case. Now I'm done talking about these two. Let's go to your semiconductors. Okay, see, let me take up germanium now. Maybe you'll understand the picture now. Okay, this is your germanium. See, or silicon. Okay, let me write silicon also is possible. This is silicon atom. I'm really going for semiconductors now. Okay, semiconductor. Okay, check now. If you have doubts, please ask me. Okay, see, so if I take a semiconductor like your silicon. Let's write the electronic configuration first. Okay, what is the silicon electronic configuration, guys? Silicon atomic number is how much?
14.
14. Okay, so what is the configuration, guys? 2 comma 8 comma 4. So 2 in the first orbital, 8 in the second orbital, and how many in the valence shell, guys?
4.
4. Okay, let me draw energy levels for them. See, as you have already learned, this is the energy level for the which electrons, guys? All the electrons are the 2 electrons.
2 electrons.
2 electrons in the first orbital. Then we have a gap, okay, between the first and the second. We have how many electrons here, guys? 8.
8.
1, 2, 3, 4, 5, 6, 7, 8. Then we have the last energy level here right now. We call it what level, guys? This is the valence, right? Valence shell, right? This is the energy level, okay? This is the energy level for which electrons? All the electrons are the valence shell electrons. Valence shell electrons. How many should I draw, guys, here? 1,
4.
1, 2, 3, and 4. Okay, this is only for one atom I am drawing. Okay, I can show you here how it looks like. Okay, it has 14 protons, 2 electrons, 1 and 2, 8 electrons in the outermost shell. Obviously, you know by now it have 4. 1, 2, 3, and 4, and they are going to stay as far as possible from each other. Okay, so that's why I've drawn in extreme points. Now, these 4 electrons. These 4 electrons are these. Okay, 1, 2, 3, and 4. Okay, so that is what I've drawn there. Okay, I think you are clear with this part till now. Yes or no, guys? Check.
Yes, sir.
Okay, yes. Okay, now I'm going to ask you a question. Think and tell me. Do you agree that this is E3? Yes, this is E2, and this is E1. E3 is the highest energy level right now. Yes, it's the highest energy level for these valence electrons. But if I take silicon crystal, or if I take silicon solid, will I get only one atom, or I'll get many such atoms? Many such atoms. Okay, because when you take a solid, you'll get many of them. Okay, so I'm going to draw one by one another one. Okay, paste. So I've taken the second atom. Okay, now you think and tell me. Let's forget about these 2 levels. They are inner electrons. I'm not worried about them. But let's go to these 4 outermost electrons here. This one, this one, this one, and this one. Please tell me, where will they have energy values? E1, E2, or E3? Where will they have energy values? E3. Agree, all of you? Check. Where will they have energy values? In which level they will have energy?
E3.
E3. Okay. But I told you just a while ago. Okay. Will these electrons have exactly same as these electrons, this electron, or slightly different?
Slightly different.
Slightly different. That's what I told you. Okay. All the electrons in a solid, they cannot have same energy values. Okay. Slightly they are going to be different because of their position actually. Okay. That's why I'm going to draw four dots. 1, 2, 3, 4, but very close to this E3 level. Okay. Like this, I think you will agree with me. I can copy and copy and paste. I think I should have one more thing. So let me just do this right now. I'm pasting some more of them, so automatically you'll see, right, we'll have another 4. 1, 2, 3, 4, 1, 2, 3, 4. Like this, we'll have many electrons here near this E3 level. Okay, now I am going to tell you what am I doing. Okay, I'm talking about this solid. By the way, I should have mentioned this earlier. I forgot to mention is this. Okay, I have to mention the temperature. And the temperature I'm talking about right now is 0 Kelvin. Let's be clear with that. Okay, what's the temperature, guys, right now? 0 Kelvin, I'm taking a solid. Don't worry, everything is fine. But what kind of temperature have I taken, guys? Any temperature or 0 Kelvin? Yes,
0.
0. Anybody who can tell me what is the meaning of 0 Kelvin? What does 0 Kelvin? 0 Kelvin has another name. We call it. We call it what, guys? Absolute 0. I'll tell you what happens in absolute 0. Okay. Well, what do you think? Absolute 0 is a temperature or a very low temperature? 0 Kelvin is like minus 273 degrees Celsius. It's a very low temperature. 0 Kelvin is like very, very low temperature. Now you think and tell me, all these electrons, they'll find it easy to move or very, very difficult to move? Outermost I'm talking about.
Difficult. Very difficult.
Very difficult. Yes, it is very, very difficult for these electrons to move because the temperature I've mentioned already is how much? Absolute 0. They cannot move at all. Absolute 0, such a temperature, electrons, they cannot move from one atom to another atom. Okay, so now you tell me, do you agree that these atoms, okay, sorry, these electrons, the outermost electrons, are they valence electrons? Yes or no? They agree or not? Are they valence electrons, guys?
Yes, sir.
Yes, outermost electrons. Agreed. Yes, but can I call them free electrons, or they are not free electrons?
Not free electrons.
They are not free electrons. I think you are clear with this one. Why they cannot move? Because the temperature is high or very, very low?
Very low.
Very low. Okay, so they cannot move. Okay, that's why. Okay, right now, do you agree with me that even if I draw a band, which is called what band, guys? Which is called conduction band. Okay, okay, but right now, so yeah, this is a group of energy levels for valence shell, though this is called valence band, and this is I have drawn is conduction band. Okay, now you think and tell me, does it look like full or it looks empty? Empty. Why? Because only those electrons I can draw here if they are what? If the electrons are bound or if the electrons are free.
Free.
If the electrons are free, they can move and give us current, but if the electrons are not free, they cannot give us what? Current. So there is no electron right now in conduction band. That's why conduction band is what? Empty. Yes. Okay, and all these electrons, what do you think they are doing? They're just sitting there, or they're forming a bond? What do you think? Yes. What are they forming here?
Bonds.
What bonds we call them?
Covalent.
Very good. Covalent bond. Do you agree with this, guys? They form what bond? They share, no? Electrons, check. I'll draw it properly. Okay, so this is the picture right now. Okay, don't forget what am I drawn. Don't forget. Okay, what have I drawn, guys? I have drawn what, guys? Silicon. Picture of silicon. At what temperature have I drawn it, guys? At 0 Kelvin. Okay, you tell me, all the bonds are intact or they are broken? All the bonds, not bones. Okay, bonds. Are these bonds broken and the electrons are free, or the electrons are not free?
Not free.
Electrons are not free.
Okay, where are these electrons present? In which band? All the electrons are present in which band?
Valence band.
Valence band. And can the electrons go from here to here or cannot go?
Cannot go.
Cannot go. Why? Because the temperature is high or very, very low?
Temperature is too low.
Too low. Okay, now I'm going to tell you something. Okay, think and tell me, huh? Do you agree silicon now is a insulator or a conductor?
Insulator.
Silicon is a insulator. Under what condition? Tell me.
Under 0 Kelvin.
Very good. Under a temperature, under condition whereby we are mentioning the temperature. Okay, silicon at a temperature of how much? 0 Kelvin. It is a insulator. And you're going to answer something more about it. Tell me why it's an insulator. Because you saw just now, right? The conduction band is full or empty? Conduction band is empty. There is no electron which can gain energy and go to which band? Conduction band. Okay. And what about valence band? Tell me. Valence band. Is it full or empty or completely full? Valence band is completely full. Why? Because all the electrons which are supposed to be in the valence band, they are present in the valence band. They are not leaving your valence band. So your valence band is full. Okay, completely full. But your conduction band is empty. Guys, did you really understand what I'm doing?
Yes, sir.
Okay. Only one response. Others, I don't know. Are there or not?
Yes, sir.
Okay. Jonavan, Jaden is clear. Very good. Okay. So yeah, this is the picture at 0 degree. Okay. Now let me show you a proper diagram. Okay. Let me do it. So see, this is not only true for germanium, it is also true for silicon. Okay. Let me bring silicon again. Okay. Check what am I doing. I'm going to only talk about the 4 electrons in the silicon again. Okay. But this time I'm going to increase the temperature. Increase the temperature. That means, tell me, what is the temperature now? Equal to 0 Kelvin or greater than 0 Kelvin? Greater than 0 Kelvin. Check how does silicon behaves. Okay, check, huh? This is okay. Let me make it like this. 4 electrons. I don't have to talk about the other. Okay, they are inside, so I am not so interesting. Okay, those electrons. Okay, so this is a picture of one silicon. Let me just copy and paste. Notice we are not in 0 Kelvin now, right now. We are more than 0 Kelvin. Okay, we are more than 0 Kelvin. I could have just copied and pasted this one. Just give me some time. Let's not be in a very much hurry also. Okay, this is the picture. Okay, check now. Okay, check. Let's just concentrate on this silicon here in the middle, this one. Okay, so this silicon, you tell me how many bonds it is forming. One covalent bond, another covalent bond, another bonding means they cannot leave now. Okay, these electrons, no, like that. See, so each silicon forms 4 covalent bonds. That is true for all the silicon present in the crystal. Okay, every silicon is almost identical, huh? So this is the picture. Can you understand this diagram, guys? Check.
Yes, sir.
Okay.
Yes, sir.
Okay, now by looking at this you can make out. Okay, tell me, did I draw any of them, any of the electrons free, or all of them are in the bond?
All of them are in bond.
All of them are in the bond. So this is a picture at what temperature?
0 Kelvin.
0 Kelvin. Okay. None of the electrons are free, but look at this. The moment I do what? The moment I increase the temperature. Now think and tell me, huh? Let me also actually I should also draw these 2 bands beforehand only. Okay, let me just do it very quickly. Oops. Okay, give me some time. So yeah, this is the energy gap. Let me just show you. This is Eg. This is the energy gap, and this energy gap is around 1 second, huh? This energy gap around, do you know about the value of this energy gap, guys? How much it is? This is valence band, this is conduction band. For silicon, I think it is around 1.1 electron volts. Okay, that is the gap, 1.1 electron volts, or it may be 0.7, huh? I think 0.7 is for germanium, electron volts, around this much. Okay, I'll tell you what does it mean. But this is the picture at what temperature, guys? T is greater than 0 Kelvin. You will get me, just give me some time. See, so please check and tell me, huh? Till now, look at my diagram. What is this diagram called, guys? This is called
Energy
level diagram, no, or band diagram?
band diagram.
Band diagram. For who am I drawing this energy band diagram right now? For
Silicon.
Silicon. Okay, if it looks like this, that means I have not drawn it for 0 Kelvin. I have drawn it equal to which Kelvin? Not more than 0, but equal to what Kelvin? 0 Kelvin. Why? Because look at this. Conduction band looks empty or full?
Empty.
Conduction
Empty.
band looks empty, and the valence band looks what? Full.
Full.
For this picture I have drawn it. See, for this one. Can you understand? This picture, this is the diagram, because none of the electrons are free, and this happens at 0 Kelvin. But just now I told you, let's increase the temperature. Let's see what will happen. Okay, when I go to this diagram now, greater than 0 Kelvin, see what will happen. Okay, check. Okay, do you agree that some of the electrons now, okay, at a increased temperature, electrons, they start gaining energy. Electrons, they do what, guys? They start gaining energy, and we call it thermal energy because of temperature, no? So they gain what energy?
Thermal energy.
And by gaining this energy, okay, what do you think? The electrons will still stay in the bond, or they can come out of the bond. You need energy to break the bonds. Okay, by the way, that's the only thing required. What do you need to break the bonds, guys? What do you need?
Thermal energy.
You need energy. Okay, now you tell me, temperature is 0 Kelvin or more than 0 Kelvin?
More than 0 Kelvin.
More than 0 Kelvin. More than 0 Kelvin means they will gain energy or not? Yes, and all the electrons will break, or some of the electrons will break?
Some of the electrons.
Some of the electrons will not break, but the bonds will break. Okay, so look at this. The electron which was present here have left this bond and it is now present inside the solid, but it is not in the bond. Can you understand? What do I call it now? What do I call it? I call it electron or free electron now?
Free electron.
Free
Free
electron.
electron. Okay, look at this also. Here also, this one. Okay, this electron is gone from here. See, so there's a gap there. I have to talk about this gap also, huh? So this electron is gone from there and the electron is appeared here. So this electron is also called what electron? Free electron. Can you understand that now we also have what electrons, guys? We also have free electrons when the temperature is greater than 0. Now you tell me what will happen. Can I say a valence band is full or it is not full? Now all the electrons are in the valence shell or they have left the valence shell, some of them.
They have left the valence
So
shell.
there's a gap. If there are 2 gaps in the valence band, that means those electrons, they have reached where now?
Conduction band.
Conduction band. Can you understand this, guys, all of you?
Yes, sir.
Yes, sir.
Okay, you can ask yourself, are these electrons free or not free? Free, because they are in the bond or they are not in the bond, not in the covalent bond anymore. Why the covalent bond has broke, right? Why? Because the electrons, they gain what energy? Thermal energy. Yes. So now I have electrons in which band? Conduction band. And now you tell me, will I call silicon a conductor or insulator now?
Conductor.
Now your silicon behaves like a, all of you are getting me? Now your silicon behaves like a conductor. But we have to tell the temperature. What is the temperature? Temperature should be greater than what? 0. Now did you all of understand or not? Silicon, what do you think now? It's a conductor or an insulator, or it has both the properties?
It has both the properties.
It can behave like an insulator also, it can behave like a conductor also, but it depends on what?
Temperature.
Very good. It depends on temperature. At 0 Kelvin, silicon will behave like insulator, but when the temperature is more, it will behave like a conductor. Is it okay for all of you guys? Just check my diagram and whatever I've taught you just now.
Yes, sir.
Waiting
Yes,
for all
sir.
of you.
Yes, sir.
Waiting. Okay, for germanium it is 0.7, the gap. Okay, and for silicon it is 1.1. So let me tell you something about this gap energy. Okay, for silicon it is 1.1. You know what does it mean? It means what? Check. For an electron to go from where to where, if an electron is going from valence band to which band? Conduction band. Can you understand what is happening, guys? If the electron goes from where to where, guys? Valence band to conduction band. Indirectly, what does it represent? It represents the electrons are still in the bond or the bond has been broken.
Bond has been broken.
Breaking, because of breaking of bonds. And how much energy is required to break these bonds?
1.1 electron volt.
1.1 electron volts. Minimum this, or actually more than this also is required. Okay, sometimes more than this, but near to this value. Can you understand this one? Idea, guys?
Yes, sir.
Okay, now check. Okay, now let me go back to this diagram and let me tell you. See, what is this now? What is this? Will I call it covalent bond or incomplete covalent bond now?
Incomplete covalent.
Incomplete covalent bond. In any incomplete covalent bond, I'm repeating again, in any incomplete covalent bond like this one, okay, you will have one less electron, right? This was the original space for the electron or not? Now is there electron or no more electron?
No more electron.
This location, okay, this location is also treated like a particle now. Can you understand? This is something new, huh? You'll never get this in metals, huh? But in semiconductors, you have to treat this location, which was supposed to be filled up with what? Electron. This location, right, which does not have the electron anymore, right? We treat it like a particle and we have a name for it. We call it a hole. Can you understand what is a hole, guys? So what is a hole, guys? Tell me.
Vacant space.
It's a vacant space, yes. A hole is nothing but what, guys?
Empty space.
An empty space or a vacant space. But is this vacant space anywhere, or it is only in a covalent bond it is found?
Only in a covalent.
Only in a covalent bond. This vacant space, which was supposed to be, this space was supposed to be filled. Okay, this one, say this one. This space was supposed to be filled with what? With an electron, but the electron has left this, right? Whenever an electron leaves this, right, you get an empty space, and that vacant space, we call it what, guys? Hole. Okay, very important concept, because these holes also will play a role in transferring of charges. Okay, let me show you here. Do you agree that here also, right? What is this, guys? What will I call it?
Hole.
It is a hole. It was supposed to be filled up with an electron, but there is no electron, so I have to call it a hole. What does it represent? It represents the empty space in a covalent bond, which was supposed to be filled with an electron, but electron has left the covalent bond, so electron has become free, so it has left behind a hole. Now this hole, I told you, right, will be treated like a what? Like a what, guys? Yes, some pay attention. Yes, you have to particle. It has to be treated like a particle. Now you cannot digest it. Okay, I'll tell you why you cannot digest it, because we cannot see it. No, that's why you cannot digest it. Okay, but I'll tell you the property. Look at this. There may be any other electron. I'm repeating again. There may be any other electron, and that electron can be attracted to this hole, and this electron can go and sit on this hole. Did I make sense? So now you tell me, this bond again can be filled up or not? Empty bond, not empty bond, incomplete bond again can be completed, because there may be some other electron can go and sit there. Can you understand this idea? First of all, this is the idea, and it is not very difficult. Okay, it is possible for electrons to go and sit in that hole again to complete that bond. Okay, but do you understand at least this idea, guys?
Yes, sir.
Okay.
Yes.
In other words, I can say that the hole must be what kind of charge? Positive or negative?
Positive.
The hole must be positive charge. Do you agree with this? Because who can come and sit here?
Electrons.
Electrons. Yes, electrons can come and sit here. The holes are given positive charge. Okay, so please remember this. That's why we treat hole as what, guys?
Particle.
Particle. Did you understand this concept, guys? Because holes are very, very important. Okay, let me go back. Let me draw silicon again. What you have learned just now is this. Silicon has 4 electrons outermost. It forms bond like this. Okay. What can happen, guys? I told you just now. This electron can leave from here, be somewhere there. When it goes there, what it leaves behind, guys, here? What is this? This is a hole. But some other electron can come and sit in this hole, right? That means the hole has the ability to attract electrons. That means it can attract negative charges. That means hole must be what charges, guys? I told you just now.
Positive.
Positive charges.
Positive
And that's
charge.
why hole must be treated like what? They must be treated like
Particles.
particles. Are you clear with this concept till now, guys? Is it okay or not?
Yes, sir.
Yes, sir.
Everybody is clear with this? Sure. Sneha is there. We are meeting after so many days.
Yes, sir.
Okay, Sneha is also listening. Very nice. Okay, now let's go back. Now you must be thinking, okay, how come hole can help us? Okay, let's go back here. If you look at the picture now, okay, check. If I draw 3 holes, okay, see, look at this. Where should I draw holes, guys? Anywhere or only in the valence band?
Valence band.
Why in the valence band? Because holes are always present in which? In a location of which band? Which bond?
Covalent.
In the location of covalent bond. You cannot draw holes here. Look at this. If this electron moves from here to here, you cannot say that there's a hole here. No, you cannot say this is a hole here. Okay. See, this electron went from here to here, right? So you cannot say this is a hole here. Why? Because holes can only be present where? In the incomplete covalent bond here. Incomplete covalent. The holes can be present here, but cannot be present here. If the electron goes from here to here, don't think the hole is here. Okay, no. So holes can only be present where? In the incomplete covalent bond. And the incomplete covalent bond, right here, this location has an energy equal to the energy of your valence band. Always remember that. Okay, so holes will always be present where? Valence band. Is it okay? Did that make sense? Okay, so holes will always be present in valence band. If I draw 3 holes, what does it mean, guys? How many free electrons are we getting? Now you can easily tell me.
3.
Yes, if we get, what happened, my pen is not writing now. Did it die off with the battery? Okay, battery also has died. I have to charge for some time. Okay, I'll take for another 5 minutes maybe, okay, for today. But at least you got the idea, at least what is conduction band, what is valence band. I'll send you these pages, you have to study today only. Then yes, now comes the main part, okay, and after that I'll stop. Why holes are important, okay, in making a semiconductor a conductor, okay? Just check, tell me whether you understand this or not, okay? Give me 1 minute to charge. How much charge is there already? 3%. Let me just charge for a bit. You guys, what do you think? You guys will be able to come offline for few
No,
days?
sir.
No, no.
No, sir.
For few
Sir,
days
online
better.
is better.
Online is better for few days, no? Let's do this only, no? What do you say, guys? All of you, no?
Don't know, sir.
Rohan is saying don't know. For few days better to do like this only, because many of you don't respond, okay? When I also ask you to come offline, you guys are not even responding. So at least online, so you are there. Many of you have joined, so it's fine.
Sir.
Yes, yes.
Sir, when you will teach wave optics?
I did not start wave optics with you all.
No, sir, you have started.
No, wave optics, so I have to teach you offline only, right? Okay, okay. ठीक है ऋषिकेश.
Yes, sir.
Wave optics is very difficult, right, to teach online. With one group though I finished. I hope so they have remembered also. I've given them the notes also. Anybody wants to collect the notes, so please remind me, huh? And then remind me, and then you come and collect the notes, okay? Okay. Look at this. This is the last part now, okay? See. So why it is so important, okay? Why whatever we have done is so important? Why semiconductors are important? See. Try look at this. What is this? A metal or a conductor, okay? We know about them, right? What do we have inside them, guys? What do we need to draw?
Free electrons.
Free electrons. Yes, correct. How do we get current, guys? In a conductor, in a metal, we have to apply what, guys?
Potential difference.
Potential difference. One will be plus, one will be minus. Who will move where, guys? These free electrons, tell me, where do you think they will move? To the left or the right?
Left.
All these free electrons, right? They start moving to the left. Agree with this diagram? Check, all of you check, guys. Yes or no? Because this side is positive, this side is negative. This side high potential, this side is low potential. Electrons being negatively charged, they move on to which side, guys? High potential, no? So this is a flow of charge or not? Yes, yes. This is a flow of only 5 minutes, so respond, guys. Yes, yes.
Yes, sir.
It's a flow of what? Flow of charge. So this is what gives you what? Current. Now you think and tell me, is there any hole here or there's no hole here?
No hole.
No hole. Why?
No hole.
Why no holes? Because did you get these free electrons by breaking the bonds, or without breaking the bonds you get these free electrons?
Without breaking the
Without
bond.
breaking the bonds. Yes, you don't have to break the bonds, okay? In a metal, moreover, the bonds are ionic bonds, no? Metallic bonds, no? Metallic bonds they call it, okay? You don't have to break the bonds, so you don't have any holes, okay? But let's look at semiconductor now, okay? Check. If I make a wire made of semiconductor, what is present here, guys? What is this? Silicon, agreed? I'm talking about semiconductor now, huh?
Yes.
Semiconductor. So it has 4 bonds. From now onwards, let me tell you, we'll never talk about 0 Kelvin, okay? Because what do you think? We will have solids in 0 Kelvin, or will not have in 0 Kelvin? What do you think? Naturally or normally?
Not possible.
Not possible, yes. Okay, so 0 Kelvin is not a good temperature to talk about. So what do you think is our temperature, guys? 0 Kelvin or more than 0 Kelvin?
Room temperature.
Room temperature, very good. Room temperature. So now you tell me room temperature. Is this the correct picture or not a correct picture? This is not a correct picture at room temperature because some of the electrons will be in the bond or they have left the bond, guys.
Left the bond.
They have left the bond. Can you understand my diagram, guys, all of you? So there's a hole here because the electron has gone there. There's a hole here because the electron has gone there. There's a hole here because the electron has gone there. So what are these now? Tell me. What do I call them? This one, and this one. Yes, these are what electrons, guys?
Free
electrons. Yes. And what is these red circles, guys? These are
Holes.
These are holes.
Holes.
Is it okay? Making sense till now?
Yes, sir.
Okay. Now check something. Okay. Check. Do you agree that this is a silicon wire? You'll agree, of course, on that. Just let me just extend it a bit more. Just be with me only for 2 minutes. Okay. If you understand, then we are fine. Okay. See. This is also silicon. It has all the electrons here. Now check. Okay, check. Tell me whether it makes sense or not. Again, I have to come and apply what, guys? Potential difference. Now looking at this potential difference, tell me, okay, the electrons will move to the left or the right? This is plus and this is minus. The free electrons, they will move, no? The free electrons, like this one, will move where, guys? To the left. This will also move to the left. This will also move to the left. Okay. Now look at this. This electron, sorry, this silicon, does it have any free electron or no free electron?
No free electron.
No free electron, right? Yes, it doesn't have free electron. But you know what can happen? But because of this minus, right? What will the minus do to the electrons here present in the bond? It will just push. It will push. Very good. Do you agree that the minus sign, right, the negative sign, right, will push this electrons or not? Which may not be free. They are not free. So look at this. What will happen now? Okay, what can happen is this. This electron can go from here and go to the left. Okay, and automatically what do you get, guys, here? What do you get here?
Free electrons.
No. Here what do you get?
Holes.
Holes.
You get a hole. And this electron which has come out from there, you know what it can do? It can go and sit. Okay, this electron can go and sit in this hole. Can you understand my diagram? What I'm trying to say? There's a hole here, no? I told you, right?
Yes.
So you tell me. Okay, electron from here has gone out from this bond and is going and sitting in some other bond, right? And I told you it's easy for the electron to go and sit there or not?
Yes, sir.
Yes. So now you tell me, is there any more hole here or there's no more hole here? Here.
No more hole.
No more hole. But do you agree with that the hole has appeared here or not?
Yes, sir.
Okay. Now my question to you is this. Okay, you must be thinking, what am I saying, right? So you tell me, okay, can I say that the hole has moved to the right or not?
Yes.
Where are the free electrons moving?
Towards left.
Towards left. And where are the holes moving?
Towards right.
Towards right. Do you agree with me? There may be another electron which will be easier for it to leave that bond and come and sit in this hole or not?
Yes, sir.
Okay, so now automatically a hole will appear on the right because the electrons have broken this bond from here and has gone to the left. So you get another hole here. Okay. Do you agree that the holes also, they play a role in transfer of charge or not?
Yes.
Yes, sir.
Yes. That is what I'm trying to tell you. Okay. Do you agree, all of you, with this one, what I said just now?
Yes, sir.
Yes, sir.
Okay, so even the holes are helping, okay, in conduction of charges, in movement of charges. Okay, that's why, you know what, see, if the electrons, they move to the left, where will the holes move, guys?
To the right.
To the right. Okay, and I need to just make sure I write it properly here. Okay, check. Okay. Check this one. This is the last thing that I'll stop, huh? So if the electrons are moving to the left, tell me, we get current due to electrons or not?
Yes, sir.
Where do you get current? Where do we get current? Tell me, to the left or the right?
Right.
To the right.
To the right.
If electrons move to the left, we get current due to electrons to the right. Okay. Where are the holes moving? Tell me, left or right?
Right.
Right. Do we get current due to holes also? Because holes are also what charge?
Positive.
Positively charged. Now you tell me, where do we get current due to the holes? To the left or the right?
Same direction.
That means it's a positive charge, no? Holes are moving to the right. Current due to holes also will be to the
Right.
Right. So now you look at these two currents: the current due to electrons and the current due to what?
Holes.
Holes. Are they in the same or opposite direction?
Same direction.
That's why they are adding up their currents. The whole current will be added up with which current? Electron currents. And this is why semiconductors are so different. Can you understand? Because in a semiconductor, not only the electrons, the free electrons, they give you current, but even the movement of what? Holes, they facilitate or they help the movement of charges. So in a semiconductor, you get current due to electrons also and current due to holes also. Are you clear with this idea, guys? Then I'll stop.
Yes, sir.
Okay.
Sure.
So any confusion or no confusion? You understood what I said just now, till now?
Yes, sir.
Okay. Next day, I think most probably we'll fix up the date. We'll meet next week also like this. We will finish semiconductors. We can finish very fast. Okay. So I'll do like this. I'll send you some notes. Okay, on this, some pages. Please read at least that much. Okay. For today, I'll stop then. Then thank you. Bye.
Bye.